question is something like this: why do the stone lying in sun gets heated up much more than water lying for the same duration of time? So stone is there and water is there, and it's under sun for the same time. Then why the stone gets heated up much more faster than water? This is related to the specific heat capacity, because the specific heat capacity of stone is 0.80 joules per gram Kelvin, and for water it is 4.2 joules per gram Kelvin. Means water requires much more heat to rise its temperature compared to that of the stone. So that is why the stone requires only this much, 0.80, whereas the water requires 4.2. So that is why the stone gets heated up much more faster than the water if both are kept under the sun for the same interval of time. So next question is, why is it not advisable to use copper as fuse wire? Now, why you don't use a copper, because which is easily available, why you don't use copper as a fuse wire? See, copper has a high, basically the fuse wire is something which is connected in an electrical circuit along the live wire, so that whenever there is a surge in current, the instrument or the device which is using the electrical energy must be safe, so that the extra sudden surge in current should not reach the instrument, which may damage the instrument. So the fuse wire should melt itself. When there is a sudden surge in current which is beyond what the instrument can handle, then the next moment the fuse wire should melt itself and the instrument must be safe. The extra current must not reach. So it has to melt itself. So it should have a low melting point. The fuse wire must have a low melting point. And normally it is an alloy of tin and lead. So its melting point is near to 200 degrees Celsius. But for copper, its melting point is some 1035 degrees Celsius something. So more than 1000. So if you use the copper as the fuse wire, the extra current will obviously reach the instrument. Even after the instrument gets burned itself, the wire won't melt itself. So that is why you are not using fuse wire or copper wire as fuse wire. Now next question is, which color has greatest speed in vacuum and also in glass? Which color? So we have the 7 colors. Out of this, who is having the greatest speed in vacuum? See, in vacuum all of them are traveling with the same speed. So speed is same for. But in glass, see, the glass is having something called refractive index. So for glass, refractive index is near to 1.5, and it provides different values for refractive index for different colors. So violet is having the highest refractive index when it passes, or violet poses greater hindrance when it passes through the glass compared to red. Or you can say the one who is having a higher frequency travels slower compared to the one which is having a lower frequency. So the answer to the question, which color has greatest speed in vacuum all are having the same speed. Which is having the greatest speed in glass? In glass, red travels faster compared to the violet, because refractive index for violet is more. So more the refractive index, lesser will be its speed. Now next question is, a sound traveling in water has a wavelength of 0.4 meters. So sound traveling through water, has a wavelength lambda of 0.4 meters, and the velocity of sound in water is 1400 meter per second. Now the question is this wave audible in air? If the same wave travels in air, is it audible to us or not? See, the audible range of a human being is from 20 hertz to 20 kilohertz. So what you have to find out is how much the frequency of sound. So how to find? So velocity is equal to frequency into wavelength. Velocity is given as 1400. Frequency is not known. Wavelength is 0.4. So you will get frequency equals 1400 divided by 0.4. So 1004 divided by 4. So you will get it as 3.2. So you have 3200 hertz as the frequency. Now when you do 3200 as the frequency, so obviously it is between 20 hertz and 20 kilohertz, so it is audible. Next question is, where should an object be placed to get an enlarged real image? Where should be an object be placed to get an enlarged real image and enlarged virtual image for a convex lens? So you have a convex lens, I should get enlarged real image also, and I should get enlarged virtual image. In both cases, where should I keep the object? See, you will get an enlarged real image. Let us see first about the enlarged virtual image. So, virtual image will be created by the convex lens when you keep the object between, this is the optical center, or you can say the pole, but normally we say pole, and this focus. So when the object is between the focus and the optical center, or you can say pole, then you will get a enlarged virtual image in case of a convex lens. So convex lens, for convex lens, if object is between F and O, you will get enlarged virtual image. Now if the object is between beyond, there is a table in your textbook which tells you where will be the image formed when you are keeping the object. So if the object is at infinity, very far away, the image will be at the focus, very diminished. As you bring it closer and closer, at 2f, that is twice that of the focal length, then you have the same size of image being produced, inverted image being produced at 2f, same size. And when it is beyond 2f, between 2f and f, so if the object is somewhere here, then you will start getting an enlarged image. So when the object is between 2f and f, you will be getting an enlarged real image, and when the object is between f and o, you will be getting enlarged virtual image. Now next question is, two waves of same pitch and amplitude have amplitude in the ratio 1:3. So amplitude ratio of two waves, amplitude of first wave by amplitude of second wave is 1:3. Find the ratio of the intensity and frequency. Now intensity of sound is directly proportional to amplitude squared. So first wave's intensity first wave by intensity of second wave is proportional to amplitude first wave squared by amplitude of second wave squared. So you can make a constant, so I1 by I2, proportionality will be converted into a constant, so it will be amplitude of one first wave squared by amplitude of second wave squared, so that will be equal to 1 by 9, because 1 squared by 3 squared. Now what about the frequency? See, the two waves of same pitch, so since they have said same pitch, pitch means which is related to frequency, so same pitch means frequency is same, so frequency won't change, so the ratio of the frequency is 1:1 because they are of the same pitch. Now next question is, which electromagnetic radiation is used in photography in fog, and why is it ideal for this purpose? So which electromagnetic radiation is used in photography during fog? And why is it useful? So we will say the answer as infrared because heat radiations are what we are using to photograph any object in fog. Now why is it is useful? Because see, infrared, so red is having lower frequency compared to other colors. Now fog, when the light passes through the fog particles will scatter this light, and scattering depends upon the frequency of light. For example, the one who is having a higher frequency will be scattered more compared to the one which is having a lower frequency. Now intensity of scattering is directly proportional to 1 by wavelength raised to 4 square. So means the one who is having the lower wavelength means one who is having a higher frequency. So violet is having a higher frequency, so it means lower wavelength. So lambda value is less. So if lambda value is less, so if it is in denominator, intensity of scattering is more, so that color will be scattered most. Now if you take the case of red is having low frequency, means higher wavelength. So higher the wavelength, the denominator value is more, so intensity will be less. So the scattered light, this infrared radiations are scattered least compared to other. So that is why we are using infrared for photography in fog, because the red lights get scattered least compared to other colors. Then if lens is placed in water, how will its focal length change? If a lens is placed in water, how will its focal length change? See, focal length and refractive index are related by a formula 1 by f is equal to n minus 1 by r1 minus 1 by r2, where r1 and r2 are the radius of curvature of the two surfaces. So in this case you have to know that if the refractive index increases, and so in air the refractive index is 1, in water refractive index is 1.5. So as the refractive index increases, so this term will increase. Refractive index increases, then this as per this formula is in 12th standard, but if I explain using that formula comes something like this: n2 minus n1 by n1 into 1 by r1 minus 1 by r2. Now n1 is that of for the air, n2 is for that of glass in normal case. So when the focal length, when the refractive index increases, the focal length will also increase.